Ladies and gentlemen, welcome back to the 29th Baltic Road Conference. Now we will start session 4/2 on road pavements and materials. I will be your moderator today. My name is Evaldas Petrikas from Lithuania, and we will have 6 speakers today. Each of them will have 15 minutes for their presentations. So we will have to end in 1 hour and 30 minutes. The schedule is very tight, so I ask speakers kindly to keep up to their allotted times. And now, first speaker to start up the session is Mr. John Laurent from Canada, who specializes in the design and commercialization of 3D and laser imaging technologies for industrial applications. Mr. John, the floor is yours.
Hello, thank you all for coming. First time I have to compete against a live band and I guess an open bar, so thanks for being here. I'm going to be talking about a 3D laser system that we developed and commercialized. It's called the laser crack measurement system, and I apologize, there's like too many slides and too little time, so I do have an article. If you read it, there's more details. Or we do have a booth here. You can come by and see us. There's no open bar, though. Here we have Pavemetrics is a company. We're located in Canada. We're a spin-off of the National Optics Institute, where this technology was developed. So we've been in operation for almost, I guess, a little over eight years now. We specialize in vision systems for infrastructures. So we have developed about 350 systems in 40 different countries that operate to measure mostly roads. We also can measure rail and tunnel infrastructures. Here's some examples around the world of different systems. We have Canadian Rocky Mountains. This is a Sprinter, Mercedes Sprinter van. This is in Qatar. I think it's the Doha airport. This one's in India on a kind of a Range Rover type thing. Australians, Italy. So we get around. I don't think we have any systems in the Baltic states. So if there's anyone from the Baltic states here, maybe you want to use this kind of stuff. We don't usually sell directly to governments or DOTs. We sell to integrator companies, so these are some of them. They will buy our systems because we just sell sensors and some analysis software. So eventually people have to actually make them work on vehicles and so on. So these are companies that do that. These are some airports also that we've done runways on, and not us, our clients. So a lot of the major ones, Gatwick, Heathrow, LA, Schiphol. These are all airports. Hong Kong isn't in there, that have been scanned using this kind of technology. So the reason why these big airports like it is it's fast. We can go 100 kilometers per hour and get all the data, and that way they don't have to close down. It's popular also because it works on all kinds of asphalt surfaces, hot mix, chip seal, like thin layer asphalt, and concrete, and porous asphalt also. So how does it work? Basically, we use a red here. There's a laser line that's projected onto the pavement, and there's a camera in blue here looking at the laser line. So if we have a flat surface, the line will be straight. Camera sees a straight line. If there's a rut, then the laser will be curved. Camera will see a curved line. So if the amount of curvature will give us the depth of the rut. Okay, and if we zoom in on this area here where there's cracks, it's kind of the same. You have a straight laser line, and then when there's a notch in the line, that's the presence of a crack point. So this technology is called laser triangulation. It's different from LiDAR. There's no mechanical parts, and we do a whole profile at a time. We don't do one point at a time. It's much more accurate also. It's a 1/4 millimeter accuracy on the vertical. And if you're going 100 kilometers per hour, we can actually measure a point every millimeter over the whole road surface. So this is what I mean by a profile. You see in blue here, there's one profile, and you see this is the data, and where there's a crack, even this is a very small crack, maybe 2 to 3 millimeters, there's a big notch in the line. So really, we just need to detect this notch, because cracks are always deeper than the surface. Otherwise, they wouldn't be cracks, right? So they'd just be surface. So by having very good accuracy and very good resolution in the vertical scale, we can automatically detect these cracks. This is very good. It's easy to detect a crack like that. Okay. So I mentioned some of these. The acquisition rate can go up to 28,000 profiles per second. That's 1 profile per second every millimeter at 100 kilometers per hour. And that's like almost 100 million points a second. So that's a lot more than a LiDAR would give you. So this is what a surface would look like. It looks really nice. We can see the cracks, and the specifications are really good. But the most important spec, it's not on the spec sheet. The most important spec is the software, the analysis software. What can the system do? So basically, we've developed algorithms that'll detect using the intensity. We have 2 kinds of data, the 3D and the intensity. So the intensity is the reflectivity of the laser. So that allows us to see lane markings and sealed cracks. And then with the 3D, we can measure macro texture and raveling, loss of aggregates, cracks and joints in concrete, ruts and potholes, of course. And then the cracks, they have to be classified. So we have 3 different kinds. It's basically pattern cracking, like alligator cracking, and transverse and longitudinal cracks. And when we add IMUs, you see we can measure IRI, road profile, and road geometry. This is an example of a crack detection result where blue is a thin crack and red is a thick one. So there's another one where we detect the edge of pavement. But what I really like is this graph. This graph gives the repeatability. So this was done by ARB, which is the Road Research Board, and they did 5 different runs going both sides of the road, and they compared the crack detection results. Okay? And when you see the repeatability, we get 98%, 97, 99, 92, 99, 96. So this is even better than my scores at school. So when you have repeatabilities in the high 90s like that, it's not, it allows you to follow the cracking over several years. You know that the data is reliable and you can compare from year to year, because when you see a variation in the measurements, it'll be a variation in the asphalt and not the fact that your instrument is unreliable. So of course, if we can see cracks, we can see potholes. Rutting also can be measured. So in the US, it's the right and left. I know here you probably do 3-meter rutting. We can also do that, no problem. Texture, we can see in this picture, there's a rough texture here and there's smooth texture over here. So now we just have to put a number on it, and the universally accepted number is the MPD. So the MPD, you take the average surface, every 10 centimeters you find the highest point, and this here is your MPD. So these were tests in New Zealand where they take a laser profiler and they scan, and then they compare to results from the LCMS data taken at 30, 50, and 70 kilometers per hour. And on different sites going from very small textures, 0.4, to large textures, 3.5 MPD, and on many different sites. And the results over here also probably A+ scores, 97% R² with the texture measurements. Okay, but what's better than a texture laser is this system actually measures texture over the whole surface of the road. So why is that a good idea? Well, when you want to find bleeding, like areas over here where you have bitumen coming to the surface, you can see if we color code the texture, we can do a texture color map. And the blue here is very low texture. So these areas we identify as bleeding. And those, of course, if they're wet and so on, they're very slippery areas. Other things we can do with texture, we can see here the very low texture associated with sealed cracks. So that helps us detect sealed cracks too. Also raveling. You see here, this is a porous asphalt road. So already porous asphalt is very textured, but when you lose aggregate, it's even higher texture areas. So we can detect those high texture areas and measure the volume of aggregate loss per surface area, giving you a raveling index. So when we do that, we can see here, this is a raveling index, and this is an example of a road section where the raveling index is low. We don't see any raveling there. You see here, high raveling index, we can see there's a lot of loss of aggregate. High, low, high, you get the idea, okay? What about road geometry? Okay, road geometry, to do that, you need to have the 3D data, but you also need IMUs, which are basically gyroscopes and accelerometers put together, 3 axes. So you have IMUs on airplanes and also in iPhones to be able to tell you how you're turning and so on. So by combining that information, here we see IMU with a laser sensor. We can evaluate how the sensor is going up and down, and we can measure the distance to the road, and then we can use the quarter car filter to measure IRI. So this is Proval. It's used a lot in the US and in Europe, I guess a bit, to validate the class of a profiler. And you can see here we're a class 1 profiler in terms of both bias and precision. What's interesting with, again, we're covering the whole surface, so instead of just a few points, so if the driver is wandering like this, we can, if you only have a 1 point, you can't do anything, but we can actually always measure the profile from a fixed distance from a lane marking, so that we can compensate for driver wander and get a more repeatable IRI, especially in network level conditions. Okay, slope and cross slope, basically it's just measuring the slope and the cross slope of the pavement. So if you do this manually with this kind of an instrument, you have a precision of about 0.1 degrees and a repeatability 0.1 degree. And when we compare to the ground truth, this is our average slope error is also about 0.07 degrees with a 0.1 degree standard deviation. So it's about the same as the ground truth for both slope and cross slope. Now, what's even more interesting is if you want to do high precision 3D milling and paving projects, well, you actually, one of the hardest parts is to get the input model to know exactly how accurate, with enough accuracy, what the road is like, okay? Because normal way is to go out and survey the road, and this takes a lot of time, and you don't get a lot of points. You know, on a kilometer, you maybe get 100 points, okay? And it takes several hours to do that. Now, if we combine the instrument, have a GNSS system, INS, with a local RTK correcting base, we can actually replace the surveyor, and the surveyor only needs to put in a control point every 300 meters or a kilometer, and you'll still get a survey grade data model. So, okay. Now, you have to compensate for all the movements of the vehicle. The driver can stop, can slow down, accelerate, turn. Right? And when you've done that, a good example is here. When we're going over a speed bump, what do we see? We see a wavy road. Now, is the road wavy, or is it just because the suspension of the vehicle is going up and down? So when you do the dynamic corrections, then you see that, okay, yes, it is a flat road. Right? Now, how accurate can we do that? So to know how accurate, we have to first compare. So we do sites that have been surveyed in a traditional method, but we also want to know what the repeatability of the traditional method is. So we did multiple measurements of these areas with the ground truth, and what we notice if you do the multiple surveys and people do it well, the accuracy is around 3 millimeters in X, Y, Z. Okay. Now, when we do the same tests, the same measurements, this was over 300 meters, these tests. So when we do the same test with the LCMS using an Planix, Pulse LV, and local base station, we get very similar results as the survey. We had 3, 5, and 2 millimeters in Z over 300 meters. And that's measuring 2 points 300 meters apart. Now, if we measure 2 points 825 meters apart, then the error goes up a little bit, 6, 6, and 4, but still survey quality. So you could have just control points every few hundred meters, just one, and it would be enough to get survey grade over the whole road. Now you have to remember, these surveys can be done at 100 kilometers per hour, so you can do it very fast, right? You don't have to spend a lot of time to do this survey. And you can do it multiple times, and you can do it before and during the construction phases, so it's very efficient. Now, this allows you also, if you're doing network level surveys for road condition, you can take that data, process it, find all the defects in the roads, put that in your PMS, and then the PMS system will have a priority project list with the road maintenance, and then you take the same data that you used, put in a few control points, and you can use it to redesign your road and then have it rehabilitated in 3D. So this is an example of a road without the geometry, and this is once you know the geometry. And just to mention, this one is an example of a bridge. See the bridge here going up, the bridge deck? It's concrete with the joint, and this is the asphalt part. And if we zoom in, you can see how well the joint is reconstructed. So really survey grade data. That's all I have. I guess we don't have time for questions. Sorry. So that's all. Thank you.
Thank you, Mr. Laurent. We do have time for one question. Does anybody from the audience? Okay, gentleman over there. Please introduce yourself and your question.
Hello, my name is George Juania from Georgia. So I have two questions. No, three questions, if possible. So first question is a short question. It is possible, this measurement is only possible in the dry, when the condition of the road is dry, or it's also possible when it's raining? Because if the driver is going in some kind of countries, it suddenly comes rain, he must stop the measurement or not. So the second question is it maybe better to combine the camera with the laser sensor? Because as an engineer, that I don't link only to this kind of graphic, that when I put my mouse on this topic, yes, that I have also the visual, what kind of problem is it? Is it possible or not? And yeah, and third question is okay, let's answer this, and I will.
I'll answer both of them. Well, first of all, for the rain, it depends how much water. If it's like big spraying water, then yeah, that will probably be too much water. If there's a lot of water, it's probably not a good idea to make measurements. The most critical thing is texture, because it increases the noise of the sensor a little bit, the water. So you would think the road is rougher than it is. The texture measurement would be the first one to be affected. The least affected would probably be if you're using it as a road model, because anyways, we filter out so many points that even if there is noise, it would all disappear. It doesn't affect the cracks that much either. the detection. So it depends on what you want to measure. As for adding cameras, like we supply these sensors, for the road surface, but we don't, like I say, we sell to integrators and they add all kinds of equipment. They will add GPR, they will add cameras, 360 cameras, they will add LiDAR, they will add a lot of other things. So yeah, for sure, you would want to have images to go with this data, yeah.
Last question, did you use this equipment only on the motorways or also in the cities?
Well, we're actually not users of our own equipment. We only sell the equipment, but yeah, it's used a lot in cities as well as highways. Where I live, Quebec City and Montreal, they're all scanned using this technology. I know Los Angeles is, and New York, so there must be many, many cities that are scanned. Oh.
Thank you, Mr. Laurent. And if we will have additional questions to Mr. Laurent, he will be after the session, and he can answer you during the coffee break. Yes, he has a booth. So our second speaker to give a presentation is Mr. Ervins Spuriņš from Latvia. He will tell us about use of ground penetrating radar 3D laser scanner system on Latvian roads. Over to you.
Hello, ladies and gentlemen. My name is Ervins Spuriņš. I'm from Latvian State's Road Competence Center, and as Mr. Moderator said, I will give a presentation about how are we using our one of our latest investments in our fleet of measuring devices, and this is a ground penetrating radar 3D laser scanner system. This story began some 4 years ago when decision was made in Latvian state roads that we will have a ground penetrating radar, and in this picture is this system that we decided that we will go after this. It's made in Finland in company Road Scanners, and as you can see in this picture, there are two systems, two blocks combined in one vehicle, and you can get in one go measurements from ground penetrating radar, which is these orange boxes in the front, and also in the rear, on the roof of the car is LiDAR laser scanner, which scans surface, and you can get subsurface and surface measurements in one go. And it took about 1 year when we did the procurement procedures and building this car, and after a year this car rolled into our backyard, and quite by chance our Minister of Transportation was there also, and he was the person who did the first test run with this car and said, yes, okay, you can use it. It will work. A little about this car. In front, as I said, there are two types of antennas. These boxes are for, mostly we are using for asphalt measurements because the depth of penetration radar is 70 centimeters, but we are using for asphalts, and these can scan up to 3-4 meters, reach 3-4 meters depth. And laser scanner can reach 15 meters in both directions from car, and we can get a 30-meter corridor of road surface and surroundings. And when this vehicle moves, then we come from this LiDAR radar, we can get a 3D model of terrain. In this picture, I have made a short comparison of summary, what are we doing with this machine, and where are we using these measurements. And as you can see, there are two main areas where we are using this for design purposes and for quality control. we are collecting input data for road designers, mostly from GPR. They are interested in asphalt concrete thicknesses. That's the main, this biggest part, but also sometimes they can they are interested in the location of underground objects, and from laser scanner we can get area of asphalt concrete and segmentation by embankment cut situations, ruts, depressions, and these measurements also asphalt concrete thickness and area of asphalt and ruts and depressions can also be used in very similar in quality control measurements. There are also one more thing we can do is void content detection, and I will in the next in my presentation I will give a short introduction what each of these measurements, how we do it, and what we get. In my presentation, I will more focus on 3D scanner because there will be also next, after a few presentations, there will be also my colleague from Latvian State Roads. He will give this GPR, tell more about GPR issues, and I will, in my presentation, focus more on laser scanner. As I said before, we have road designers are interested in areas of asphalt because we have quite a lot now objects where we are doing milling and resurfacing this road, and then you have to know the area to plan the cost of the job and to tender out precise area what will have to be done. And from laser scanner, we measure, old school way was that the road engineer was crossing this road with measuring wheel several times and writing down this distance in his paper sheet and then doing these calculations. And it's take times, it's not safe because of high volume roads, traffic volume roads, you have to cross the roads. It's not a very good idea, but we can just drive one time in traffic speed and doing these measurements in traffic speed and get we can see in the laser picture this boundary of asphalt, and then we can measure these distances. It is done automatically, and you can get this distance, this road width, and then from this, it is very easily, it can be calculated area of this asphalt. Next thing is also from, if we put this information from laser scanner height data on color map, then from these colors, it can be possible to detect if we have on an embankment or it is cut or like in this place there is zero embankment or these blue dots, it means there is vegetation. Red color, we are in the cut, and blue color, it means that we have embankment, and it is very valuable information for road designers because each of these road sections requires different approaches sometimes, so this is also what they can get from this laser scanner picture. And also we can get, if they are interested, cross section in every place where they want, and it's possible to do actual measurements, for example, this embankment height, and they get this input into their designs. There was this next one where we used this ladder was case. It was done only once, but also I just included it in my presentation because it just shows how versatile this equipment is and how much you can do from it. And this was the case when our old profiler was not available. it was some technical problems, but there was quickly we needed to measure there is depression in the road. It is about 30 meters, this section, and we needed to calculate the volume of this depression because to need to know how much material we need to get to fill it. And usually when we are doing measurements with this laser scanner, it scans road crosswise, but we don't have a precise EMU unit, and we cannot, from these measurements, get the road profile. And what we did in this situation, we rotated this laser scanner so that it scans road longitudinally, and it gets these profiles every 10 centimeter steps. And when we combine these measurements together, then we have a very good can read the depth of this depression, and if we know the depth and the width of the road, then calculating the volume is just simple mathematics. There are also one interesting case that over the years, next to the road, between the road and the ditch, there over the years accumulates soil and vegetation starts to grow, and of course it makes water barrier, and water cannot get from road to the ditch. It starts to penetrate into the road construction. Of course, water and the roads, it's not very good friends. And this have to be removed, and it's nice to know how much you need to know and how much trucks you need to buy services, and how much this will volume of this work will be. And from laser scanner, there we have a cross section of the road. And here you can see this water barrier, and if we make this imagined line, and also with taking some mathematics to help, then we can calculate this volume in every 10 centimeter. We can make these measurements every 10 centimeters on the road, and combining these data together with distance, we can get volume of this, how much we need to remove this. Unfortunately, there is some cases when we need to use this tool also for road defect investigations, and it's when the road is newly constructed. Thanks God, it's not very often this happens, but sometimes it happens, and then we also using this device. For example, here is one case when was newly that was done only asphalt recycling, and put over it 2 layers of asphalt, and very quickly started to develop ruts. And the contractors was sure that it's coming. The problems are coming from some subgrade, because he was working only on the top layers, and he said that there is weak base. But we did measurements with falling wedge deflectometer, and it didn't show any problems. But when we looked at these laser scanner pictures, where there is very easy to see that the road contractor was working in these segments in different times. He was not making all road in one go, but it was divided into segments, and then you can see that these problems are correlated to these sections. For example, there is some sections where there is no problems, and there is some sections, and these boundaries of these problem zones is corresponds to these end on beginning of this section. And from this picture we can deduce that the problem was because when it was made this asphalt was recycled, it was not compacted properly, and then it was not weak sub base, of the road the problem, but the problem was the compaction of this recycled asphalt layer. And also in this problem investigations we can do ruts, we can measure ruts, but not only ruts. If we do this, for example, over the few years, then we can see how these ruts are developing, because we also here laser scanner can detect this road center line, and he can then correlate this data precisely to this line, and we can get very precise the same location, and we can see how these ruts are developing, and we can measure this by number, and also we see this picture. And that's the short information about what we have done in these years. Thank you.
Thank you, Mr. Purinch, for your interesting presentation. Is there a question from an audience? One question, please. Only one? No? Okay, so thank you very much. And you will be able to ask Mr. Purinch questions after the session. And I would like to invite our next speaker to speak about application of GPR, Estonian experience. This time it is Mr. Marek True from Estonia. Please welcome, the floor is yours.
Good afternoon, ladies and gentlemen. My presentation is about Estonian experience and practice in about pavement density and air void measurements with ground penetrating radar. My name is Marek True. A good pavement density and suitable air void contents are very important factors in achieving a waterproof pavement, especially in Nordic freeze-thaw conditions. In Finland and in Estonia, pavement upper layer density and air void content, which is a function of the electricity, is nowadays measured using appropriate GPR techniques. Electricity of pavement, again, is a function of the electricity of its components, its aggregate, its binder, and its air, and their proportion in pavement. So we can see changes in quality with GPR. Traditionally, pavement density and air void content is measured in a laboratory. It's through core sample volume and weight compared to standard laboratory compacted samples from the same mix. As GPR measures only the electricity of pavement, data from core samples become even more important as being the reference for the calibration. Why we love GPR? It's safe for the worker. It's continuous, giving and continuous data. It saves traffic. You don't have to stop any traffic for measurements, and it's non-destructive. No core drilling. Okay, that's not really true. We need a reference course. For example, measuring of density and air void content in 10 lanes and joints of airport runway is possible during one single night window. A little bit about history. The first GPR was brought to Estonia for road measurements in 2000. It was bought from road scanners, but I had to say that for air void measurements and density measurements, the system was not really widely used. Before 2016, density and air void were usually measured from 12 core samples per kilometer, but that represents only 0.001% of the whole pavement. But since 2016, GPR is widely used to measure varying core density and air voids, and this already represents about 10% of the pavement, which is about 10,000 times more than with coarse samples. The original method development of air void measurements started in Finland from the initiative of Timo Saarenketo. He's in the conference, I know, and he's here. Great. And after some studies, the method was announced by Finnish standardization organization, a PANK, in asphalt areas. It's from 1999. And as much as I know, this method was upgraded in 2008. Method for Estonia is based on this method, this Finnish method. After studies that were carried out by Tavi Duntz and others, I'm not sure if he's here, somewhere in the conference anyway, the method was modified in some extent, and it was taken into use in 2001 in Estonia. But the main finding in the studies was that we need more core samples that on that time it was in Finland for calibration. So it was set that 10 samples from the pavement lane and 4 samples from pavement lane and 4 samples from joint are needed for proper calibration as minimum. Double measurements in some sites recently indicated that pavement electric values increase, and this means the air voids decrease very quickly after paving. So it was observed, and we found that this can be reduced. This effect in measurements can be reduced if we do the measurements between wheel tracks instead of in wheel tracks like we did before. And sometimes we face the issue that the calibration suffered for correlation between average and point calibration coefficients. And the new procedure was established for calibration in order to minimize this effect. Based on some studies we did in 2014 and 15, new requirements were established in 2016. For some requirement, for example, for measurement repeatability, which was not regulated before, you have to do parallel runs and to show that it's the same. A new calibration procedure, just told before. Requirements to testing laboratory. It cannot be any laboratory. It has to fall in certain requirements. The measurements between wheel tracks, already said. New requirements to reporting to cover all necessary information for the supervisor, for example, or client finally to make the decisions if the results are good and if the measurements are done properly. And also dealing with cases where measurements are not possible, for example, because of the weather reasons. And a little bit about the reporting. It's very important to have a very good idea immediately when you look at the reports that what are the results? Is it good? Is it bad? How to read it? We found that one of the very important and very easy to read graph is a histogram of the values of the air voids and density values. The results should be seen immediately. We should see if the results are good. For example, here we have a density example with the distribution, and with green color you see that it's in good condition if you set the proper thresholds, and also you have the graphical representation about the results. You should also see if there are problems. For example, here are the air void content information, and you can immediately see if the problems are there, and what is the histogram presentation, and where are the problems. Even more, you want to analyze the data. You want to see exactly where are the problems and understand what might be the cause of these problems. For example, in this page you can see that in some places we see on regular basis we have high air void content areas, and these actually reflect the truckloads. And this is something you can see with GPR, but not with other methods. To explain further this, here we have air voids compared with thermographic system. With the blue line, you see the temperature drops in the places where the truckloads used to be on paver. And on the orange line, you can see the air voids and the pavement. You can recognize definitely how these match. And coming closer to the end, some advantages and disadvantages wrapped up in one page about GPR and traditional method. Told already, the GPR is much safer. It's continuous measurement. It's almost non-destructive. It's non-destructive. And the measurement is fast in traffic speed. The small disadvantages are that it still needs calibration. What can we do? We need calibration, and this calibration is very important, how to do it. In traditional method, okay, I forgot to tell that also there are some issues which are which are not really often thought about, especially because traditional methods don't give this information. But with GPR, you can understand that there are some issues, the more issues that affect the data quality. For example, the homogeneity of properties of mixed components, and especially aggregate, are actually quite important. In case of GPR, the part that is important is ER values, it's the electricity values. But the same homogeneity is an issue also in traditional method, but you don't see it so well. But for traditional method, the good point is a very good accuracy in single measurement. The good accuracy in single point measurement, provided that you have the reference data of the mix from the same point, especially in case when the mix is not so homogeneous as we could expect. And the disadvantages, of course, are that these measurements are time-consuming and expensive, needing traffic closures. It reflects only a tiny area, and it's not possible to get location-based understanding of the problems, for example, and to evaluate the effect of truckloads or something like that. And again, the quality issue of the homogeneity of material. It's not very often understood that for the calibration of, or don't call it calibration, but to determine the air void content with traditional method, it works very well if you have homogeneous material, the aggregate that is with the same density all over the site. If it's not, the accuracy is getting down. And conclusions. Measuring of pavement density and air voids with GPR has over 15 years of history in Estonia and is now widely used since last year. as several improvements in method have increased the reliability of measurements. Thanks to continuous data from GPR, this method also helps to understand and bring out the shortcomings in density and air void measurements as such. For example, the homogeneity of aggregate properties has influence in results in both methods. And for homogeneous pavement properties are essential for high quality pavement, it's a good idea to measure this continuously and motivate the use through smart motivation system that is also known as bonus-malus system. Thank you very much.
Thank you very much, Mr. Marek True. And does anybody from the audience have a question for Mr. Marek? Thank you. Our next speaker to give a presentation on additional insights on the use of ground penetrating radar in determining pavement layer thickness and void content is Mr. Aldis Zalaiskans.
Hello, everyone, and I'm from Latvian State Roads, Aldis Zalaiskans, like you see, and the topic is the use of the ground penetrating radar in determining pavement layer thickness and void content in the Latvia, our experience. Firstly, I can say that this is my master thesis, and the conclusions are very similar like our Estonian colleagues. Firstly, yeah, like already said, it's very important to know the right dielectric property of the material we are making in the place we are making the measurement, and the same goes with the air voids. You need to know precise dielectric value of the material, otherwise the measurement will be the results will be not so precise. So this is our, like my boss Ervin Spurin said, this is our tool from 2014, and my master thesis were made mainly with these two antennas, 2 GHz antennas, and they are perfect for pavement measurements because the results are very precise. There is, here you can see one radarogram and all layers in the road structure, and the bolded one, for example, is the bottom of the pavement. The thing with this ground penetrating radar is that you know only the time when this electromagnetic wave is reflected from the, for example, in this case, bottom of the road pavement, and you need to know the right dielectric property of this material. In this case, asphalt concrete. And to know that there is 2 methods we used and compared afterwards. The first is we made a lot of drills, like 90 drills, and after that we made a laboratory testing for them for void content to determine the right what's the right void content in that point. Marked the drills, and after that made measurement. The other method is metal plate testing, which is possible with this device, and it gives the dielectric property of the material by itself with the calculations what is made in the program. Here you can see the measuring process. The first antenna here, radiogram, second radiogram, and the third is the dielectric property of this every scan, dielectric property with the metal plate testing. Here is the mark of the drill. You can see there a little bit, maybe you saw it, and we compare it. For this research, we used 3 locations in Latvia. The construction, in the all sites, construction sites, the construction works were similar. And the first one is on the road A1, second one is on the road A2, and the third is on the road A9. And the results, in this graph you can see pavement thickness with both methods. The red line represents metal plate testing. In metal plate test, what's the getted dielectric value, and the calculated in the blue line represents calculated dielectric value in the drills, and compared. In the 2 of our 3 sites, the results were similar like this. There is like 2 and more centimeter error, and but what's interesting, in the third construction site, we found out it's very similar, and we asked the question, why is that? And the reason is because the first 2 layers, for the first 2 construction sites, the first 2 pavement layers are the main mineral material dolomite, and the top layer is the main mineral material granite. But for this third construction site, all 3 layers, main mineral material are granite. And that's the reason why the results are so precise. And in this case, you can use only, to determine pavement thickness, only metal plate testing, and there's no need for drills. You can maybe put, for example, 1 drill for checking the results. But for the iron voids, there were like more interesting results, and we found out there's like, if you want to know for all pavement layer iron voids, even with the drills, for example, theoretically, the points should be like in this line. If the iron voids raises, then dielectric value goes down, because dielectric property for the iron is 1. What is the minimum of the, even in the all dielectric property scale? And but the points are like in the cloud, and there is no correlation in the red dots represent for all 3 layers together. And with this metal plate testing, the points should be like the same, but you can see there is like small correlation, but you can see something here. And this is made with metal plate testing, and compare the iron voids in the top layer. Very similar results goes with the second construction site, and the third, where all layers were with the granite, there is some correlation, maybe seen barely, but you can see here is point, like they should be like this. And if you want to know, like I already said, all iron void content in all pavement layer, in this method, I think it's not possible in my studies. And we ask why is that? Because it should be like very easy. If the iron goes down, the dielectric value goes up, and the reverse. And why is not in my results, for example? The main thing is like my colleague already said, this material should be very homogenic because otherwise there is like differences between dielectric property in it. You can very clearly see it here when the one part of the results are like down, and this is the results with the metal plate testing, and that's because in every day they make asphalt concrete in the factory. They mixes the new asphalt like every day, and they can be slightly changes in the materials. For example, the granite can be a little bit different, and the dielectric properties will be a little bit different too. And what we can see in these results, but it's the same road. It looks totally the same from the surface, but in the results there is like difference, and we found out the same thing like my colleague from Estonia. There is like from the truckloads, there is some kind of air void error. It can cause some errors too, yeah. But we need like maybe research more to find out what's more can cause these air void errors. Yeah. Yeah, here. And to summarize this, I can say that dielectric values determination with the metal plate may not be used for calculations of pavement thickness if layer materials are different. Exception is the case when all layers are made of the same aggregate. It may be concluded that dielectric values of asphalt concrete layer is significant influenced by aggregate content. And the next one is conclusion that this our GPR method can be very easily used because there were like slightly small changes in the dielectric properties and the drills, and it can be used with our Latvian condition by correlate these results with the drills very easy. And like I already said, there is almost no correlation between air voids and dielectric property in our pavement layer, and you can see smaller correlation, like some correlation you can see in the upper layer of the pavement in our case. Okay, thank you for attention. Yeah.
Thank you, Mr. Zalaiskals. Are there any questions for our speaker? Thank you.
Thank you.
Our next speaker is Ms. Carmen Kut from Estonia. She will give us a presentation about predictive modeling of road friction based on macro texture and road PMS data. Over to you, Carmen.
Hi, I'm going to give you a brief overview of a study that we did with my colleagues and I on predictive modeling of road friction based on macro texture and road PMS data. So, as most of you probably know, road friction is an important parameter when it comes to road safety. Several studies have shown that low road friction especially is related to accident rates. Road friction is mainly influenced by the state of the road, whether it's wet, rainy, dry, has slush on it, and macro texture and micro texture of the road. Also, some studies have found a link between the aggregate materials used in asphalt and road friction. But although road friction is an important parameter, measuring it is quite time-consuming. This means that doing it on a network level is expensive, or at least it's not very cost effective. On the other hand, measuring parameters like macro texture is quite cost effective, and in many places, including Estonia, it is already done on a network level. So this is why we posed the following question for the study. How can we measure road surface friction based on the parameters of macro texture and road PMS data? How can we find the sections where road friction is actually problematic without having to measure it? The structure of my speech, or the presentation here, is quite the same as the accompanying paper. I'm going to start with giving you an overview of the methodology we used. Then I'm going to jump straight into the results that we got. Firstly, giving you the overview of the models that we built based on our test sections, and then on the results we got from actually applying those models to Estonian road data. Then I'm going to give you a small map that shows the problematic sections, and then I'm going to conclude with giving you the conclusions from the study specifically, and then some questions that were still left in the air after this study. So the methodology that we used was that we firstly gathered road sections to measure. We gathered around 200 kilometers of roads, mostly around Tallinn, and there were around 15 distinct road sections on those roads. We measured macro texture and friction on those roads, and then we gathered the macro texture and friction results with the PMS data that we got about those road sections, mainly the age of the pavement, the type of the pavement, the aggregate materials used, but also the traffic intensity on those roads. And then we tried to create different models. We started with linear regression models and linear regression trees, and then we did classification as well. We did logistic regression, for example, and we did decision trees. For the decision trees to work, we actually needed to use two mathematical methods on the data to artificially create more problematic road sections, because the traditional methods did not work, since we only had about 3% of road sections of the entire data where the road friction was actually problematic. So the methods weren't able to predict on such a small sample of problematic sections. So the results that we got. Firstly, the results that we got from the models. Firstly, we saw that linear regression models did not work, or at least they did not give us any sections that were actually problematic on those test sections. The reason for that was firstly the aforementioned fact that we only had 3% of the road sections that were problematic of the whole 200 kilometers that we actually measured. Second thing that I haven't written down, but is probably true as well, is that there might not be a linear correlation. The regression models don't work if there is no correlation to speak of. Secondly, what we did was we found that most of the models that we built relied heavily on only macro texture measurements, and they didn't really include the other things that we were trying to include, namely the parameters from the PMS data. This was especially true for the legit models, where including the parameters did make them a little bit better, but not by a whole lot. Thirdly, what we saw was that most of the models greatly overestimated the problematic sections on those roads, meaning that they predicted a lot more sections where road friction was problematic than we actually had problematic sections. This means, on applying them on the level that where we applied the models, is that these models cannot be used alone, but they're more of an indicator of problematic sections. They can't be used without actual friction measurements. And fourthly, what we saw was that it was quite difficult to find a balance between sensitivity, precision, and accuracy on the models. The following graph will illustrate this. What we see, for example, the first bar chart is the decision tree. The decision tree had a very high accuracy and it had quite high precision, but it lacked in sensitivity, only finding about 50% of the problematic road sections. This, in reality, made the model, though it had the highest precision, practically unusable because it missed a lot of the sections that we were trying to find. So what we had to do was we had to use models with low precision but high sensitivity, because they would at least find many of the sections, though a lot of the sections would also include places where road friction was not problematic. So then we started applying the models. We chose 3 models from all of the models that we tested. We chose those models based mainly on 3 factors. We considered sensitivity, as mentioned before, and accuracy. But what we also considered was that these models would be quite different from each other, so that they would predict on different parameters. And we could then look at what those models that were different, how the things that they predicted would match. So the table below shows the percentage of the road network that each of those models found to be problematic. It varies between 7.5% for one of the decision tree models to 3% on the logarithmic regression model. The road sections that matched across all of the models were 2.5% of the entire Estonian road network. So this map now illustrates the road sections in Estonia that all of the models actually found to be problematic. What we can see is that mostly these road sections are longer sections along the same road, which actually makes a lot of sense, since most of those road sections are built during the same time, which means it has a lot of matching parameters in regards to age of the pavement, but also the materials used. So it would make sense that that longer sections would be found potentially problematic. So what were the conclusions that we actually drew from this study? Firstly, we saw that these models can be used to narrow down on areas where friction can be problematic, but they cannot be used alone without friction measurements, since they do overestimate a lot of the problematic sections. But it does help us to find out areas where it would be smart to measure friction, where it could be problematic. Secondly, we found out that using other variables besides macro texture can, in some ways, improve the quality of the models. We found that, especially including the age of the pavement and also the measurement period, improved upon the baseline model that only included macro texture. Thirdly, we found that mathematical methods, as the Smoot and Rosé method that we used, were quite useful in creating a better quality model. For our case, it improved upon the fact that we were actually able to predict more places where road friction can be problematic. But I could also see those methods being used in other road survey and road issues, for example, like road accidents, where the percentage of where we are trying to predict something that happens very rarely. So some of the issues regarding to predictive methods that still were raised even after the study. Firstly, we found that additional measurements could have greatly improved upon the models, especially if they were done over shorter sections along roads that were built during different times. We could have greatly improved upon the base where we had more variance in the data from the PMS. And that could have improved upon the quality of actually including the PMS data, because all of the models greatly, as mentioned before, relied on the macro texture results. Secondly, what definitely requires more research is combining different models to create one better model. Currently, I know that there are startups out there, especially in the financial sectors, that are using several less accurate models and combining them into creating one accurate model. And this could be used here as well, or at least this way of thinking, of taking several models that are less than ideal and using those models together to create a more accurate model. But again, this requires a lot more research. So thank you, and if you have any questions, I'd be glad to answer.
Thank you very much. Are there any questions for our speaker? Thank you. Our last speaker this session is Mr. Pauli Kollisoja, who is professor at Tampere University of Technology in Finland. Mr. Kollisoja will answer us a very important question today. How will the roads survive after the super heavy trucks started to operate on roads? Over to you.
Thank you, Mr. Chairman. Good afternoon all. I was a bit worried to being the last speaker and going to have the least audience, but I'm happy to have all you here. So I have a bit of a challenging question to be answered. Much of the research work I'm going to present are done in close cooperation with the Finnish company Road Scanners that has already been mentioned a couple of times in the earlier presentations of this session. And the co-author of this paper, Petri Varin, is also coming from that company. So the outline of my presentation, a little bit background regarding laws, then I'm going to discuss about the potential effects, what the changes that have taken place in the regulations may cause and may lead to, and then something about the investigations and conclusions that we can draw until now. A bit less than 4 years ago, we got a new law on allowable truck weights, and the maximum allowable truck weight was increased from 60 tons to 76 tons. There was also increases in the allowable total weights of a group of 2 or 3 axles. And then there was fortunately, there was a rule that 65% of the total mass of a trailer must be resting on dual wheels. That was a big discussion and also lobbying issue during the lawmaking, and one part of our study is dealing with that. With special permission, super heavy trucks with the mass of even exceeding 100 tons are now operating on our road network. But those exceeding 76 tons are only allowed on special roads. This 67 ton is allowed on all road network, including all the low volume roads what we have. Allowable axle loads as such were not changed, and there has been quite a bit of misuse of the so-called fourth power law. You may know that the loading effect or damaging effect of an axle is related to the fourth power in relation to some reference axle. So if we are not increasing the axle loads, our road damage should actually decrease, because there are less truck weight to carried by the road to transport certain amount of goods. But that's not the truth, because if we have a group of 2 or 3 axles, we don't have 2 or 3 separate deflection bowls. They are traveling in the same, more or less in the same deflection bowl, and the loading effects are summing up. So definitely the road distresses are increasing when the allowable axle loads on a group of axles are increasing. This kind of things we are now having on our roads. 11 axles, 92 tons, 13 axles, 104 tons, on special transportation defined roads. The loading, one of the changes that is taking place is that we are having more axles following each other, there is less wandering of the wheel paths, and that's an important issue. Then this 65% rule, if it's really necessary or not, that's an issue. Potentially there are quite many mechanisms that can be affected. I would say that the 3 first ones showing up as rutting of the road surface are much related to the decreasing of wheel path variation. Here I just would like to refer to the presentation Antti Vehviläinen had yesterday morning regarding the autonomous trucks. If those and when those start to operate, then we are in an extreme situation where the traffic, the wheel path wander is non-existing anymore, and then these mechanisms will increase a lot. If we have a thin road structure like on a low volume road, then even also the single wheel, dual wheel issue will affect the subgrade, but mostly it's related to the behavior and performance of the upper part of the road structure. Pumping effect I will discuss a bit later, and also some special issues like culverts. I will go through these things very quickly because there are 2 papers on this research published in the Transportation Research Record. So this is a test site where we wanted to have a further proof on the need for or if the dual tires are needed, is this rule required. Basically we were measuring having pressure cells at different depths below the road surface, and then we were measuring the deflections of the road surface. This is, I would say, a pretty typical low-volume road in Finland, a thin soft asphalt concrete surfacing, and then about half a meter of structural layers. There was also some initial rutting already existing there, about 20 millimeters deep. We were testing, comparing dual wheels and then 4 different types of single wheels, starting from 385 to 495 in terms of width of the tire. Loading arrangements was such that we kept the truck was kept the same all the time, and we were changing the tires into the trailer, in which the front axle had a 10-ton axle load and the rear axle had 8-ton axle load. Just an example of the comparison of the loading effects. Here we have the stresses measured under this is actually from the front wheel of the truck, and then loading effect caused by dual wheels. So we clearly see a difference between the peak stresses what we have, and actually here we see that the loading effect of of the dual wheels is not quite symmetrical, and that's due to the initial rutting what we had in the road surface. So the difference would have been even greater if we had a more flat road surface in our experiment. This table is trying to summarize the differences in the measured responses. So we, as a reference case, we kept the dual wheel with the 10 tons axle load, and then compared the measured vertical stresses and the road surface deflections to that loading case. So it seems that if we have a narrow, I would say old generation type of a single wheel, then the difference is like 25–30% in terms of responses. But if we have a new generation type of single wheel wide base, so-called wide base tire, then the difference is not that much anymore. Basically, it's not so much due to the width, but more it's due to the optimal inflation pressure that's much lower in this new generation single tires than what is the case with the old generation narrow single tires. Also, even if the axle load is lower, but we have narrow single tires, then the damaging effect is more. So this is interpreting the measured responses in terms of a sort of a loading equivalency factor, and we see that it's can be up to 3 to 4 times more damaging effect with narrow single tires than what we have with dual tires. The same results that has been got many times again earlier. Regarding culverts, we made some measurements with different types of culverts, not on a very deep installation depth. Again, instrumenting for changes in the diameter, vertical and horizontal diameter, and then also on the wall strains. Pretty close, clear conclusion from those experiments was that regarding culverts, the truck is passing over axle by axle, so it doesn't mean what is the total mass of the truck. Quite a logical conclusion. Bridges, they are a different story because then the total mass, of course, concerns. Luckily, this type of picture was already explained in the second presentation of this session, these colorful maps. This is a result from rut development follow-up measurements made by road scanners again. By time, we hope we will get some more accumulated information on the loading effects of roads that are more used by these super heavy trucks and less used by them. Of course, it will be pretty difficult to define exactly what is the effect of the increased weights, but this is sort of a side product. Upper part of the picture is indicating location of steel nets that are essentially put there to prevent frost heave cracking. That's a typical problem in our Nordic conditions, but it proves out to be a very efficient means of reducing the rut development also. So here in the lower part here, we see that if we have steel nets, then very little rutting, but without on those sections there are no steel nets, then rutting is much more. Another similar example as a side product of these rut development measurements indicating the risk of leaving a old asphalt concrete below an added aggregate layer. There seems to be a section built like that and very rapid rut development in 2 years and on that section in comparison to the other parts of the same road. Finally, A few words about pumping effect. What I'm meaning with it, that if we are driving with a heavy vehicle on a soft subgrade soil that is yielding or deflecting, and if it's wet, like peat subgrade, then the water easily can escape upwards into the structure. And if we have more and more following axles, this effect will accumulate along the truck. This is the first experiment site what we made these trials, and it proved out to be that the maximum rut depths shown in the lower part of the picture here, where the rut development rate was like 1 millimeter per overpass of a truck, so pretty rapid deterioration of the road. This picture is again analysis made by road scanners. GPR analysis analyzed the attenuation of the CPR signal when it's reflecting back from the road structure. And again, the more red or black color you have, the more moisture you have in the structure. Each one of these 5 pictures is a longitudinal cross-section of our measurement area. So here's the groundwater level, the black area. The GPR doesn't see actually below that. Interesting area here is that as the number of overpasses is increasing, the red color is increasing in the upper part of the road structure here. And this is the part of the test section where we had this very rapid accumulation of the permanent deformation. So clearly shows that the reason also why what water was pumping up into the structure and structure was losing its capacity. The same was also indicated in the thermal images. The color of the rut development area changed due to the water pumping up and having different temperature than the rest of the structure. So finally, to my conclusions, these dual wheels definitely are needed. Culverts are not an issue. Steel nets efficient to prevent rutting, especially on soft subgrade areas. Aggregate layer, placing an aggregate layer in between pavement asphalt concrete layers, it's not a good idea. Pumping, especially on wet soft subgrade conditions, that's a big issue in the future. Not to speak about platoon driving, if as was mentioned already yesterday, that if we have more than one truck following each other, then this accumulation will be even more. Another group in our university has been studying these economic effects, what have been achieved with these super heavy trucks. The savings has been less than was promised in the lobbying time. There are savings and there are savings in carbon dioxide. So these heavy trucks, they have come to stay. That's our conclusion, even though they are most likely increasing our damages on our roads. So it calls for our innovations to make the roads survive. So hopefully we are not going to have too much roads looking like this. So questions on this?
Thank you very much. Okay.
Thank you. So you confirmed that economic effects in big trucks and damage to the road is less than the economic advantage from the trucking sector?
At least the costs are from different wallets. it's pretty hard to make an exact calculation on how much is the cost of the damages, and to compare to the savings in the transportation costs. So I made an exercise, sort of rough calculation exercise, that if we were using the whole savings that have been achieved and are going to be achieved in road improvements, then even the effect would still be pretty low. So from national economy point of view, I'm afraid that these savings are not as big as the losses in road maintenance, but the important issue is that they are coming from different wallets.
In parallel, we have at the moment discussions still on the Fail Baltic project, and there the effect was said to be in the socio-economic part, which is not directly calculable.
And the emission of carbon dioxide, that's an issue that I'm pretty sure will keep these things on our roads, and so much of the vehicles have already been technically changed so that we can't, I think, step backwards. So they have come to stay.
Thank you, Mr. Kolsoja.
Yeah.
Ladies and gentlemen, now it's time to finish our session. I would like to thank once again our speakers for very interesting presentations, and also thank you for the audience for being here. Now will be the coffee break, and at 4 p.m. the closing session will start. Thank you.